Swayam Prabha. Digital India. Educated India.
So we'll have the last talk in this session. So it's going to be it's going to be development of unknown identification capabilities of chemical process fault diagnosis using autoencoder generative networks. Okay, over to you.
Hello, can you see my screen?
Yes.
Okay, and I'm sorry for my video cannot be shown because I have no camera. So I'm going to presentation now. I am Wen Li from the National Tsinghua University Chemical Engineering Department. Today, I am going to introduce my research topic with you. My topic is development of unknown identification capabilities for chemical process fault diagnosis using autoencoder generative network. This presentation will be divided into 4 sections. First, I'm going to introduce what is unknown fault detection and what's the benefit of using deep learning models. Second, I'm going to discuss the method of solving this topic and the methods. The third part is the discussion of the result, and the last part is the Q&A. So first, let me introduce what is the unknown fault detection. Fault diagnosis is crucial to achieving a smart factory, as it can identify which faults occur in the early stage of process deviations, avoiding accidental plant shutdowns, improving product quality, and reducing losses. And for unknown fault identification, this is a challenging problem. For statistics process control, although unknown fault can be diagnosed, they cannot classify with known fault, and there are a chance of false alarm. In a traditional deep learning model, it has a good accuracy in the known faults. However, the model is a data-driven model, so it cannot identify the unknown category without the unknown data. So a quite straightforward thought is to generate the unknown data to help the deep learning model to learn the known fault and classify it as the unknown category. So what's the benefit of using deep learning model to identify the chemical process fault? First is the early detection. We can detect it in the early state of the fault occurs, which can reduce the cost and the risk of the plant shutdown. And the second is the improvement of accuracy. We proposed a autoencoder generative network, which by including this generative data, we can improve the known fault accuracy, which can reduce the incorrect level. And for the unknown fault, we are able to let some of unknown to identify. And the last is the adaptive, because the deep learning model can be retrained with the new data, so it can perform better by time. And next, I'm going to talk about the methods we use in this research. First is the autoencoder generative network. And next is the attention multi-text learning classification model. Third is the dataset we use is a 10S process. And first, I'm going to talk about the autoencoder generative network. We can see the model in the left-hand side. We can see in this part is the encoder with the one layer of GRU. And for the hidden state, there are the dense layer with the 2 dimensions. And for the decoder, there are 3 layers of the dense. And in right-hand side, we can see how we train this model. By input the trained data of 2 kinds of known faults. We are using the autoencoder generative network to reconstruct the trained data. And by calculating the reconstruct loss, we can let our autoencoder generative network to generate data as same as the trained data. Next, I'm going to talk about how to generate the unknown fault data. By doing so, we need to input the 2 types of known fault data into our already trained autoencoder generated network. After input into the encoder, we can get the hidden state of the known fault. In the left-hand side, there are the figures to visualize it. In this red circle, there are red spots, which is represent the hidden state of the known fault 12. And inside this green circle, there are the purple spots, which is represents the hidden state of the known fault 0. So after knowing these 2 known fault has clustered into 2 clusters. So how to generate unknown data? Our thought is that only the data point that is near the known fault is usually confusing the classifier to classify it as unknown. So by generating the data around this unknown hidden state, we maybe be able to let the classifier know what's the boundary of the known fault, and beyond that boundary, all of them should be considered as the unknown fault. So our next step is to generate a hidden state around the known fault. And we can see in this graph, the green circle and the red circle are our generated hidden state. So by putting it into the decoder, we can generate the unknown fault data frames by reconstructing. After we have discussed a way to generate the unknown data frames, next I'm going to talk about the classification model we're using here, which is an attention multi-text learning model. In the left-hand side, there is a known fault classifier. In the right-hand side, there is a unknown fault classifier, which you can see as a known fault classifier plus 1 category, which is the unknown faults. So our concept in here is that the data we have generated in the autoencoder generated network is based on our known fault. So it must have some similarity between the known fault and our generated unknown data. So we think we can use the known classifier to let the model to learn which known fault data has the most similarity to this unknown fault data. And we hope the model can learn the unknown data under. Next, I'm going to introduce our dataset, Tennis-Eastman process, which is Dawes and Bogle based on simulate data of the actual process of Eastman Company in Tennessee, USA, which contains 5 units: reactor, condenser, separators, strippers, and compressors. There are 8 chemical pods from A to H. Among them, A, C, D, and E are the main reactors. B is an inert component. G and H are the products. F is a byproduct. In this dataset, there are 41 process monitor parameters and 11 operating variables. In the dataset, the one run of data is 500 sampling points, which the sampling frequency is 1 every 3 minutes. The value occurs 1 hour later. In this dataset, there are 21 votes in total. We can divide these votes into step change and the random variation, or the slow drift and the sticking. And others is like the unknown or the constant position. And to our unknown vote detection, we choose the 3 different types of votes as our known votes. It's the vote 2 and vote 12 and vote 14. As for data preprocessing, we use vote 0, which is the normal data, to standardize our vote data. And after that, we drop the data before the vote happened, and using the moving window with the step equals 1 and the time step equals 20 to split our data into 461 moving windows per vote. Next, I'm going to discuss the result. For autoencoder generative network, in the left-hand side, we can see the lost spot versus the epoch. The model is trained successfully. And in the right-hand side, the upper row is our input data windows, which is the ground truth. And the second row is our reconstruct data window, which we can see the reconstruct plot is quite similar to the ground truth, but without the noise. So it can consider it has ability to reconstruct the known vote data. And next is the result of the attention multitext learning classification model, which includes the generate data from the autoencoder generative network. In the left-hand side, we can see the trained data completion matrix. The known vote of the vote 2, 12, and 14 is performed good with around 99% of accuracy. But for the unknown vote, only around 75% of unknown we generate from the autoencoder generative network can be learned. In the right-hand side, we can see the test performance of this attention multitext learning classification model, which we use the ground truth of the vote from 0 to 14. And we can see the known vote can achieve around 99% to 100% accuracy, which is quite good. But the unknown vote, we hope we can identify it only around 20% of it can be identified. So the way we generate the data should be improved. In UMAT projection, in the right-hand side, this is our trained data set, which is include our generate data from the autoencoder generated network. The generate data is labeled as the pink. In training, most of them can be classified as unknown. And for this region, we can know that the attention multitext learning classification model seen this region as unknown. So for the test dataset, the most of the ground truth and unknown data in the tennis isthmus process are compressed in this region. However, we can see this region in our trained dataset, it's labeled as the vote 12. So that's why we can see the result of the most unknown vote will be classified as the vote total. So for the conclusion, the way we use the autoencoder with the two-dimensional hidden state maybe is not enough to generate the data between the known vote and the unknown vote. So the better way to generate data should be proposed. At last, special thanks to my two advisors, Professor Yao and Professor Kang, which helps a lot in my research. In recent research, we have proposed a new way to generate data by using the sequence-to-sequence. In our former research, it has a good ability to generate the known votes. So we hope in near future we can use it as the way to generate the unknown vote and to improve the result of this research. Thank you for your attention.
Thank you.
Hello, everyone. My name is Chu Guanshen, and I am a
Thank you for the talk. Speaker is online. So any questions?
The attention, the autoencoder has learned the process data with quite averaging the whole process from the level to the steady state. So I think the autoencoder cannot learn the full process developer. So some window will be confused and not so accurate to the real process window.
Okay. Thank you. Any other questions? Okay, if not, we'll thank the speaker again. Thank you. And
Thank
that closes this current session. And we'll have a tea break followed by a hall 3. What is the next topic? So the next topic will be in advances in optimization in this hall. The first talk will be by Professor Bonwin, and it will be in person. Okay. Thank you.